you. Thank you for your introduction. My name is Oudriss. I'm assistant professor at La Rochelle University and associated to Laboratory LASI. And today I want to talk to you about the grand boundary character and the implication of this defects or this grand boundary on hydrogen embrittlement, and more particularly on the diffusion and trapping of hydrogen. And I will show you some results about the fracture assisted by hydrogen in a relationship with grand boundary. To start my talk, I think it is not in the full screen. The context of our work is about hydrogen embrittlement. As you can see here, this is without hydrogen, with hydrogen. We have transition from the ductile fracture to the brittle or intergranular fracture in the nickel or nickel alloys. And we can explain this phenomenon according to several mechanisms. Can talk about head and help, or hydrogen-enhanced decohesion, or hydrogen-enhanced localization of plasticity, or the vacancy formation enhanced by hydrogen. Our work is to understand what is the implication of the hydrogen and defects, metallurgical defects interaction on the fracture, on the damage mechanisms. And I show you here the nice figures made by our colleague Koyama. He resumed all the different defects in the microstructure, and our idea is to study H interaction between the hydrogen and H defects from the surface to the bulk. We can talk about dislocations, vacancies, we can talk about grand boundaries and precipitate. And to do that, we used multi-scale approaches here, using experimental techniques and modeling approaches, and from the structure to the atoms. And we need to question clearly what is the interaction between hydrogen and H defects. The topic of today, or my talk today, is about grand boundary character and the contribution of this character or grand boundary character on the hydrogen embrittlement, on the hydrogen diffusion and trapping in nickel and nickel alloys. Show you here this is preferential intergranular corrosion. And they observed here this preferential intergranular corrosion along the specific grand boundary. We call him the random grand boundaries. And other colleagues, they observed the preferential creep damage along the network of the random grand boundaries. Why we use this approach of the grand boundaries to understand what happened with hydrogen, more particularly in the nickel alloys. To do that, we have several approaches here. And the first, we characterize the microstructure. We elaborate a different microstructure. We can talk about models and model material or industrial material. We characterize the microstructure, texture, grand boundaries, and the grand size. And by using SEM EBSD, by TEM to characterize dislocation structures, precipitate and different defects at this scale, and of course other techniques by chemical composition and other internal stresses and and vacancy concentrations. For the hydrogen, we used several techniques: electrochemical permeation for hydrogen diffusion and trapping, thermal disruption spectroscopy to quantify the hydrogen and to identify the hydrogen states in the materials, and the GDOS to characterize the hydrogen profile, not to quantify, but just to have the profile of hydrogen, as you can see here. And recently, we compared this SKPFN with GDOS and with the TDS, and we have good correlations, and it's possible to map the hydrogen distribution and using the potential, surface potential, and of course we can evaluate the hydrogen profile using this SKPFM. About the mechanical part, we used a different scale. Show you here nano-indentation, tensile fatigue, and nano-indentation, tensile fatigue, ex situ and in situ. And another systems that we developed here, that we can perform the electrochemical permeation under hydrogen, electrochemical permeation under tensile test. This is for oil and gas company. We developed that, and we have very nice results for that. For the modeling part, we use the finite element method for hydrogen diffusion and interaction between dislocations and hydrogen, and of course local approach of fractures, atomistic calculations for the diffusion of hydrogen along the grand boundaries, and the DFT or ab initio calculations. Now, my topic is about grand boundaries, and then I can show you here about the interaction, the impact of the grand boundaries on hydrogen diffusion and trapping, and then I will show you some results about intergranular fracture. For the diffusion and trapping, we published it 10 years ago. this paper. On this paper, we performed we elaborated a certain microstructure of polycrystalline nickel with different grain size, and we performed electrochemical permeation for H1. And using EBSD, we separated special and random grain boundaries according to the CSL definition, very simple one. And what we observed according for the electrochemical permeation, that we have the increase of diffusion coefficient with the fraction of random grain boundaries, which suggests that we have short circuit diffusion along this family of grain boundaries. On the other side, we observed the increase of trap sites, densities, with the fraction of spatial grain boundaries, which suggests that spatial grain boundaries constitute preferential trapping zone for hydrogen. Now, to complete this study, we performed some local analysis to use coupling tough seams and EBSD. And for the same microstructure here, you can see here we characterize a different part of the microstructure of nickel polycrystalline nickel. We can by EBSD to identify the grain boundary character, double definition, spatial random, and then we completed by twin, coherent and uncoherent twin boundaries. Because in spatial grain boundaries, 80% of spatial grain boundaries is the twin boundaries. And we pre-charged our samples, and we performed tough seams to obtain the hydrogen distribution map in the same zone characterized previously by EBSD, and we performed the profile of hydrogen profile by tough seams to analyze the hydrogen along the grain boundaries. We do it for the several samples, and you can show you here example of the hydrogen concentration profile obtained. For the spatial, we have gradient, and for the random, sometimes we have some gap. We do that for more than 300 grain boundaries, and we have some statistical analysis here. And what we observe, this is different configuration that we observe, and here you have the number of the grain boundaries that we. And for random grain boundaries, we observe the gap, but we have some desorption of hydrogen, which means that we suggest it's probably the diffusion of hydrogen, but we are not sure. But the measure results observed using this analysis here is for spatial boundaries, grain boundaries, and we have high fraction or high number of grain boundaries, spatial grain boundaries with this profile, or gradient of hydrogen diffusion, which suggests is trapping zone for hydrogen. And by taking in spatial grain boundary, we separate them by twins, and twins, coherent twin boundary, and others, and coherent twin boundaries. And for coherent twin boundaries, we have majority of this grain boundaries incoherent, excuse me, is gradient. And the majority of coherent, we have nothing. I mean, that's like matrix or like grains. Now, what is the contribution of the twins in the spatial grain boundaries? To complete this approach, we perform some atomistic calculations from coherent twin boundaries to the symmetric uncoherent twin boundaries. And we identify the minimum energy path for the hydrogen to move from the bulk to the grain boundary, and from the grain boundary and to move into grain boundary. What is the energy necessary for that? We have 0.5 for in the coherent twin boundary, and for the which means that is more easy for hydrogen is to move to the coherent twin boundary and to move into the coherent boundary. But in the case of incoherent, symmetrical incoherent grain boundary, we have here it's 0.4 is easy for hydrogen to move from the bulk or for the grain to the grain boundary, but it's so complicated and high energy here for the hydrogen to move into the incoherent grain, which means which explains this gradient profile observed by Sims. And to continue our approach, we perform some experiment in the big crystals, and we have here different big crystals, coherent twin boundary, and sigma 5 and 2 sigma 11. I give you only simple definition of the grain boundaries according to CSL, but in reality we have 5 parameters to define grain boundary. And if we can give you, for example, for sigma 11, we have 2 configurations here, which means probably we don't have the same behavior with hydrogen. And what we performed hydrogen charging, sample hydrogen charging, and we compared with single crystal with same orientation, the same time, the same conditions. And here we perform TDS to quantify the hydrogen, or what we observed for sigma 3, we have slight effect. We have it's the same concentrations. For sigma 3, and for this sigma 11. But for sigma 5 and second sigma 11, we have the decrease of the concentration in the big crystals. And I'm showing you here, we do it for different time of hydrogen charging. This is single crystal, this big crystal, sigma 11, this one. And clearly we have a clear decrease of the hydrogen concentration. Now, to complete that, we perform some calculation to identify the energy and excess free volume. This is another definition of the grand boundary. And by performing this calculation, we identify for H1, H configurations for big crystals, the energy of or excess volume is the same. We have linear relationship, excess free volume, and we have a good correlation between this difference between the single crystal and big crystals and excess of free volume, which means that it's not the question of sigma or orientation, or it's question of the energy or excess free volume of your grand boundary. Now, what about intergranular fracture assisted by hydrogen? What we performed, we take only for several grain size, and we pre-charge it at very low concentration of hydrogen, and we perform the sample tensile test. And here I'm showing you here embrittlement index, this engineer approach. And what we observed, I'll show you this embrittlement index as function of random grand boundaries. And clearly, what we observed is an increase of sensitivity to the hydrogen embrittlement with the increase of random grand boundaries, which means that these random grand boundaries constitute the weak phase and is more sensitive to the hydrogen. And we have the same mode of damage, intergranular fractures. We associate that with head model, hydrogen enhanced decohesion. It's true for the low concentration of hydrogen. We do it only for one. We complete our result by the result of Bechel from the US. And what we observed here, this is elongation ratio. You have here the material with the high fraction of spatial grand boundary. At low concentration, we have good strength against hydrogen, very good. With material with high fraction of random is not really good, but by increasing here the concentration of hydrogen, we have decrease of the properties or elongation ratio for the more strength materials. How we can explain that? One of this we supposed is probably is the consequence of vacancies, because the hydrogen enhance or favor the formation of vacancies. As you can see here, some colleagues from Japan observe it for the high conditions or for extreme conditions, and we observe it here for the electrochemical conditions in polycrystalline nickel. We have a linear relationship between the concentration of vacancies and hydrogen concentrations, which means that it's not second mechanisms to take involved here for to induce the hydrogen embrittlement. I want to finish just one results we obtained a few weeks ago about antagonist effect of the hydrogen. The idea now is to identify the microstructure, the best defects or the best metallurgical elements to create or design the new microstructure to prevent hydrogen embrittlement. But now we talk about hydrogen embrittlement, but in another situation it is possible for hydrogen to enhance the mechanical properties. What we observed, what I'm talking about antagonist effect of the hydrogen. What we performed on the nickel alloy, WASP alloy, with the gamma prime precipitate, we performed different agent treatments to have several precipitate size, to have different domain of hardening precipitate here. Domain of shearing and domain of R1. And we characterize, of course, different microstructure. We characterize the precipitate, chemistry, and all that. And of course, it's good to have nice precipitate to increase the mechanical properties. This is why. And we perform the hydrogen charging. We pre-charge our sample. And of course, we characterize the mismatch of the precipitate with the matrix. And for different from different precipitate size here. And we perform the hydrogen charging, and we analyze the hydrogen concentration. I'm showing you here the hydrogen concentration as function of time of hydrogen charging. This one is for nickel single crystals. This one for Inconel 718. And you have here for only one time. We do it for only, and we have different points, which mean that is depending on the size of precipitate, we have different maximum concentration that we reach here. And by taking this concentration here, we represent this concentration as function of precipitate size, and you can see we have an increase of concentration with precipitate size, elastic field, and used by precipitation. We are in this domain, and here we have a decrease. Is another domain, and we have probably here, this is shearing part, elastic field, and here probably we have GND and geometric necessity dislocation or defects. What is the consequence on the mechanical properties? Hydrogen charging, nano-indentation, tensile test. What we take two microstructures, two precipitate size, small and large, 10 nanometer, 40 nanometers. This is diameter. And for reduced modulus, honestly, we observe any significant effect of hydrogen on the elastic modulus for the both. But for the hardness, this is another point. For the small precipitate, we observed a slight softening. And for a large precipitate, we observed a clear hardening effect of the hydrogen. We performed tensile tests to confirm these results. And what we observed here, this for small size. And clearly, without hydrogen and with hydrogen, we observed this slight softening and an increase of elongations. And here, for the large size, we have hydrogen embrittlement. Really. We have a decrease of elongation. These are new results. I'm sharing with you. I think we can discuss about that. And now to conclude and some perspective, the idea clearly is to understand the impact of the grand bandu character, the impact of precipitate on the mechanical properties under hydrogen. And thank you for your attention.
Thank you for the